we are doing lesson 3.5, which is exponential and logarithmic models. So basically, we're going to be solving some exponential and log equations, which we did in 3.4, but just like applying it to application problems. Math in real life, as I like to say. All right, students are working on this warm-up problem. Find the missing value assuming continuously compounded interest. That's our PERT formula. My initial investment is $1,000. That'd be my principal. My annual interest rate is 3.5%, so 0.035 as a decimal. We're first going to figure out how long or time it takes for our investment to double, which double 1,000 would be 2,000. Okay, and then I just told them to solve this equation. So divide both sides by 1,000, you obviously get 2. Okay, the next layer I need to take off is the base E. So what would I do to both sides? Natural log. Good. Natural log. Logs undo exponents. So anytime you have an exponential equation, meaning your variable is up in the power spot, we use logs to undo that. All right, so the natural log of 2 equals 0.035t. So to solve for t, I would take the natural log of 2, divide it by that decimal. I got a little under 20 years. Our time is in years for these models, and they gave us the annual. Okay. Amount after 10 years, that's kind of going back to when we originally did these problems, to figure out your amount and your count after 10 years. Our initial investment is still 1,000. Our rate is still that 0.035. So after 10 years, I times that by 10 in my power spot. Okay, so make sure you refresh yourself on how to type that in your calculator. Just do 1,000 e to the power of 0.035 times 10, which is obviously just 0.35. I got about, and for the money ones, I was round to the nearest penny, $1,419.07. Okay. I like this example as our warm-up because we've done problems like this before. And now we're going to do problems like this because we know how to solve equations where our variables in the exponent spot. That's basically what we're doing today. There's like a lot of different application problems. Okay, so there are some kind of like generic models. You know how when you do like linear growth, you have the classic y equals mx plus b as like your linear model, okay? For exponential growth and decay, I'm not a big fan of how your textbook lays this out because you can use this equation every time, and if your b, if this number comes out to be negative, basically like if your exponent's negative, we have exponential decay. If your exponent's positive, we have exponential growth. Think of why this makes sense with transformations. You don't have to write this down, but here's my base E normal function, right? My natural base function. If my exponent's negative, what transformation does that do to my graph? There's a negative with the x. Reflects over the y. So now it becomes decay. All right. So you don't really have to memorize per se. I'm going to give you the I'm going to give you this equation, this one. But these are really the same thing. Just if your exponent's negative, then we're going to have decay. Okay. So sometimes we'll have to solve for this b value. Your textbook uses the constants a and b. A, this number right here, is always going to be your y-intercept or your initial amount. I'm going to call it initial amount because we're doing the application problems. We're not graphing right now. Our initial amount, let's talk about y. So I said this is also the y-intercept. So if I were to plug 0 in for x, b times 0 is 0. What's e to the power 0? 1. So you're always going to end up with whatever this number is as your initial amount or like your y-intercept. And this would work actually for like any base. Okay. Sometimes, like in PERT, this factor that's being multiplied to your exponent can sometimes be like a rate. That kind of just depends on the application of the problem. Now, the other three, there's three here, models, you would never have to come up with these equations yourself. The application problems would like give you this model, and like you might have to do like a little bit of like number crunching or solving, but I'll kind of just explain what each of these are. This Gaussian model is basically like a classic like bell curve, and there's pictures of it on the next slide, but these are like commonly used in like stats. So maybe just put like used in statistics. We don't do a whole lot with this one. I don't even think I put one of these in our notes. Logistic growth model. This one's commonly used like in populations to model. Used in populations to model this growth or decay in that case, depending on the population. And then we can also have logarithmic models, and I kind of mentioned like exponentials are way more common in real life and in application problems, and we don't do a whole lot with logarithmic models. That one you don't really need to notice. You just have to like recognize maybe on a graph what these look like. Okay, so we're very familiar with obviously exponential growth and exponential decay. We're going to be using our natural base because that occurs most commonly in like real life. So I kind of just talked about how, exponent's positive, exponential growth, exponent's negative, exponential decay. Okay, here's that Gaussian model. So you can see, have you guys ever looked at like a bell curve at all for like standard deviation? Okay, what'd you say? An AP Psych? Oh, cool. So this we call like a bell curve. And basically, this like value in the middle here is like your mean or your average. So if I took maybe your test scores, let's do this, and your average is a 93%, that means 50% of you were higher than that, and 50% of you were lower than that. And I could plot all your test scores, and it would kind of form something similar. It's not always a perfect bell curve, but it can be modeled that way, because obviously that's right in the middle. Okay. I think there's maybe one problem we'll do with that. So obviously you have your log ones. Don't worry too much about those. Here, so this one I said is the one that's often used in population. So sometimes we have this capacity that's graphed with a horizontal asymptote. You won't have to graph any of these by any means. But we're just taking a look at some basic common real life applications of exponential growth and log growth as well. Okay. So exponential growth, let's start with the easy ones, the money ones, because we worked with these before. All right, this one's a little bit different. This time I don't know what my annual percent rate is, but they tell me, they don't tell me, but we're doing compound continuously. I stole this problem from the same directions as this one from the warm-up. So find the missing value, assume continuously compounded interest. I probably just forgot to recopy and paste that over here. Okay. So obviously my PERT formula uses that natural base E. This is an example of exponential growth. Right, I have my base E. P, I have my initial amount, my principal, how much I'm putting in. And then I have my rate times my time. Here's what we know. We know our initial investment is $750. That's my principal. We don't know our rate. That's what we're trying to find. We haven't done one where we had to solve for the rate yet. And we know it takes 7 3/4 of a year to double. Okay, well, obviously double 750, that'd be 1,500. And then remember, our time is in years. So you can either keep it as a mixed number or you can do it as a decimal, 7.75. That'd be 7 3/4 of a year. All right, now we have kind of a similar setup to the one in the warm-up, but now I have to solve for my interest rate. So same thing, I would divide both sides by 750. I would get 2 equals e to the, I'd probably write 7.75 r. Natural log of both sides. All right, divide both sides by 7.75. Let's do that. Natural log of 2, close, divide by 7.75. All right, I get 0.0894. Yeah, we'll write it as a percent. So I would write it like this. Oh, wait, I'd probably do it up here. 0.0894 dot dot dot, which means our rate is about 8.94%. Okay. Good problem. So I kind of have seen one of each. One where we have to solve for our amount. This one's just plug and chug, the amount after 10 years. So this one you would just take your principal. Now that we know our rate, times it by 10. Now what I would do, this is probably a good spot to show you this. What I would do is try to use as exact decimal as you can when you're calculating this. So keep that decimal in your calculator. And then do 750 e to the power of second answer. Feed in that long decimal. We want to try to be as exact as we can. Times our time, which was 10 years. Now, if you just use the rounded answer, let's see how close we get. It's probably close, but let's say we just did like 0.0894. Okay, it's about $1 off. So use and be as exact as you can. Does that make sense? So use that like second answer tool in your calculator, and that'll just feed down that decimal. All right, so $1,834.37. Okay, so now we've kind of re-looked at our PERT formula, exponential growth model, and we've been able to solve for the rate and the time now, and also the amount in the account, which we've been able to do that. Okay, let's look at a different type. This one's not so much as like an application problem, just like coming up with a model. So this is really similar, like back in Algebra 1, where I give you like 2 points on a line, and it said like write the equation of the line. Here we're going to write the equation of this exponential function. All right, so this is the formula I will give you, the classic like generic model for exponential growth, and this works for decay. All right, you really only need to memorize one formula, is this right here. A, my initial amount, e to the bx, where b is some like constant or some factor. It can be a rate if we're talking about application, but if that value is positive, we know we're going to have exponential growth. If that value comes out to be negative when we solve for it, we're going to have exponential decay. Now, looking at my graph number 1, I obviously have exponential growth, right? Do I know my initial amount?
0.
Yeah, right? My initial amount or my y-intercept is 1. So here I know A is 1. And then I also know this random point, 310, that's on my graph. So So I'm going to take my model here, and what I don't know is what this B constant is. But I'll take my model, I'll plug in this point, just kind of like you do with lines, where y is 10. A is 1, my y-intercept is 1, e to the b, x is 3. So we know that value, and now we can figure out what b is in order to write our model. All right, so just cleaning this up a little bit, I have 10 equals e to the 3b. What would be my next step in solving this? Natural log, you betcha. All right, so b is the natural log of 10 divided by 3. Okay, so I got this decimal. Okay, so similar to when you write equations of lines, you have to like solve for the slope, solve for the y-intercept, and then you write it, and you only keep like the y's and x's, right? So when I want to write the model here, now e is embedded in our exponential model. You want to only have y. We know a is 1. You don't really need to write that there. I want to plug in b. And you can just round for the model. You want to just have like x's and y's. Remember, e is really a number too, so it's technically not a variable. That would be an example of an exponential growth model. How do I know this it's growth? My b value came out positive, right? So that's why this model works, because if you calculate it and you had exponential decay, that b value would come up negative, and then you just plug it in. Yes? Well, it's just 1, so you can if you want.
So like normally we should. It goes like 2 or 3.
Yeah. Yep. And we're going to do 1 actually next here where a is not 1. Okay. Now this one's a little more challenging. Well, first of all, looking at my table, is this exponential growth or decay? Growth, right? My values are getting bigger. Do I know my initial amount? No. I don't know what a is. I'm just given 2 random points. Okay? So we're actually going to have to solve for a, and we're going to have to solve for b. Oh, this is fun. Okay. So let's plug this first point into my generic exponential growth model. So when y is 100, we don't know what a is, we don't know what b is, we know x is 2. And then if I create like a separate model here, plugging in this point, we'll end up having 2 equations with 2 variables. So this one has a y value of 300 equals a e to the b times 4. All right, I would just clean these up a little bit, and I'm totally fine with you writing this right away as just like 2b or 4b. You know, you guys recognize that, but just for sake of our notes showing what we're plugging in where. All right, I have 2 equations with 2 variables. Think that back to algebra 1. How do you solve 2 equations and 2 variables? Okay, set them equal to each other. That's kind of like a form of substitution. Like if you have y equals something and y equals something else, you could set them equal to each other. What's that other like method? Elimination. Substitution's way easier here. Okay, so I can't set them like equal to each other per se because this one's equal to 100 and this one's equal to 300. But what I could do is solve this one for a and then substitute it in to this one. Okay, so we're going to do a little classic substitution. All right, to solve this equation for a, we'll divide both sides by e to the 2b. So a is 100 divided by e to the 2b. It doesn't matter which one you solve for a. It just works out a little bit nicer to do my first one. So we're going to take this. We're going to substitute it in here. And guys, you only have to do this if you don't know the initial amount. Okay, when you have two basically like unknowns. If you're given the initial amount, you really only have to solve for the b, that factor. But this is fun. Okay, 300 equals 100 over e to the 2b times e to the 4b. Okay, so this is really like over 1 if you want to think of it that way. But if I have e to the 4b divided by e to the 2b, what would that simplify to? E to the 2b, right? Exponent properties, same base, you could subtract them. Or think you have like, 4 of them upstairs, 2 of them downstairs. So that would give me to here. And now you're like, okay, I just have b, so now I'm able to solve for b. Once I find b, then I can figure out a. All right, and that's what substitution allows us to do. Okay, divide both sides by 100, we get 3 equals e to the 2b. Then what would I do to both sides? Natural log. All right. So I have b is the natural log of 3 divided by 2, which is approximately, what did I get? 0.5493. Okay, so you kind of want to circle that. If you want to get a template of your model started, you're like, okay, I know b is 0.5493 to the x. Now I still need to find my initial amount, my a. Well, classic substitution, once you find your first answer, like when you did this with linear systems, once you found like x, you have to find the other ordered pair, you gotta find y. You can just go back and plug it in to that nice nifty equation that we solved for right here. And that'll allow us to find a. Ooh, let's use the exact value here because this will be fun. You have e to the 2, I'm going to use this, natural log of 3 over 2. And then I have 100 up top still. All right, so let's talk about what cancels here. First of all, I have 2 divided by 2. So that's just 1, right? And what? Oh, it's not bad. It's just, it's a lot of work. It's a lot of steps. But what happens here? What's e to the ln of 3? 3, right? Matching bases, so let's undo each other. So a is 100 thirds. That'd be our answer. I'm gonna move this guy down a little bit. Oh no, it doesn't want to come there. Okay. So here be my model.
Did you do the decimal of the a, or you want it in a fraction?
Since this one's a repeating decimal, since this is a rational number and it can be written as a fraction, I'd write it as a fraction. This is irrational, so that one you can like leave as a decimal. And typically, actually, this is a good question. Typically in exponential models, because these are often rates, these factors, they're more commonly written as decimals. Good question. Like that. Okay. That was fun, huh?
No.
Okay. I liked it. This one's fun too. Let's talk about population. Now, I mentioned that often used in population is this logistic growth model. This one says it follows the exponential law. So it's just our classic exponential growth. And again, I'll give you guys this formula. Okay, here's what we know. The population of a Midwestern city, probably Fenimore, follows the exponential law. The population decreased from 900,000 people, okay, never mind, not Fenimore, to 800,000 people from 2003 to 2005. Express n as a function of t. Okay, so they want us to, oops, I used x and y. That's okay, we can adjust that. Basically, they want us to write the equation or come up with the equation ourselves. So to make this easier on ourselves, we can decide what we call year 2003. We could call that our initial year. We could call that year 0. So we know in 2003, let's call that year 0, and then we'll know what our initial amount is. And that's okay, because we can just say that t is the year since 2003. We can do that. What was my population in 2003? 900,000. You can either just do 900 and write it in terms of 1,000. I just did it as 900,000. Okay. Now, in 2005, the population decreased, so we're going to have exponential decay here. So 2 years since 2003, or 2 years later, now my population is 800,000. So you're really just kind of given like 2 points on an exponential graph. We know A is what? 900,000 is our initial amount. So this one you don't have to do all that fancy substitution. We can plug in this point in for x and y. So 800,000 equals A, our initial amount is 900,000. E to the B is what I'm trying to find. And if I'm using that point, x is 2. Then we solve for B. Divide both sides by 900,000. We get 8 ninths equals e to the 2b. All right, same steps. Natural log of both sides. You guys are probably getting bored of this. We end up getting B is the natural log of 8 ninths divided by 2. Okay, hopefully you're okay with me jumping there. So we just did a ton of examples. I'm going to type this in our calculator so I can show you. Natural log of 8 ninths, close, divided by 2. We end up getting a negative value, and that makes sense. The K, exactly. That's why you don't need to know 2 separate models. It'll come out negative if it's decay. And our population's decreasing, so that makes sense. All right, now let's use our correct variables like I forgot to do. So it says express n as a function of t. So n of t, representing my number of people or my population, is 900,000, my initial amount. No, probably. I'm not too picky about that, but I should say when I tutored in college math, all their assignments were online, kind of like, have you ever done Alex? And it will mark you wrong if you don't use the right variables. And like somebody's just like, oh, it's so annoying, I did all the math right. I'm like, yeah, but also like the letters do make like matter, so I can see why they're being picky. So just, I don't know, have it something that you're conscious about, but like I'm not too picky about it. Maybe I should be. T. It is good to, use T, because then it helps you follow up with like, when will, T is question mark, like what is the time? If you use X and Y, you might get confused on like which one means what, but. All right, follow-up questions. Now that we came up with the model, so there's just this first part. I guess I could have called that part A, but there's our model. So now A says, what will the population be in 2007? How would I figure that out? Okay, why 4?
Because it's years from 2003.
Right, we called it year since 2003, right? That's what we decided. So we just plug 4 in for our time. Good. So my number of people, 4 years from then. All right, you can try to type that in your calculator. We're going to obviously round to the nearest person. That's what I got. Yep, sorry. Okay. When will the population reach 500,000 people? Ooh. Now we don't know what time is, but we know our number of people. That's N of T. So we're plugging 500,000 in for my number of people. It's kind of like the ones with the bank ones where we know the amount. We're trying to find the time. And now, and wait, didn't we do problems like this where it was like estimate the time it would take for the amount in your account? Didn't we do that?
Yeah.
And I was like, someday we're gonna know how to solve exactly. Today's the day. So exciting. We use logs. Okay. So divide both sides by 900,000. And sometimes, you know what trips people up with application with model problems is real life data is not nice numbers, okay? And that's fine. But it's all the same steps. You're just taking off the layers around x. I see a base e, so I want to take the natural log of both sides. All right, I'm just going to jump here. So we've done a lot of these now. At our time would be the natural log of 8/9 divided by that nice long decimal. All right, now here's the answer I got, and I'm not sure if I used the rounded one. I can't remember. Or if I used the exact.
8/9.
5/9 is what I got. I don't know why I put 8/9. I have 5/9 in my notes. I don't know.
That's already
Every dash mark's got to be red.
Just trying to make you guys feel better when you make mistakes. Make you feel better about yourself. Yeah. Wait, sometimes my finger works as an eraser. I don't understand this board.
Silencio la comida.
All right, that's a 5. Okay, that's a 5. All right, this is what I got for a number. I guess I could do it on my graph real quick. I probably use the exact because I usually like to do that.
We always have some little bit of leeway in these problems.
Yeah. So here's the exact, right? So I probably did the natural log of 5/9 divided by that answer. There's that number. Okay, now, remember, this is years since 2003, so we can round this up. It's really close to 10 years after, so what year? 2013. What a great year. That's when I graduated high school. 2013. Great year. Okay, what do we got for time? Just a few minutes?
No time.
No time.
3 minutes.
Yeah, we better stop there. We'll finish these up tomorrow.
Enough time for one of those homework quizzes.
Easy there, Washburn.
My chemicals are at
Listen, this guy's gonna want to have us work until